Hello YouTube, welcome to my channel. When we are given a DN model, we would like to understand how efficient the model is. The efficiency of the model concerning the computation complexity and also the memory consumption. Uh, Normally we have a different metric for both. For the memory related metric, we're using the model size. This is related to the number of a parameter and also the precision we're using. Another thing memory related is the total activation or peak activation. Total activation is mainly concerned in training process because we need to save all the activation for backpropagation, and peak activation is mainly concerned in the inferencing. Uh, Computation-related metric including MAC, flop S, op, and op S. Flop S and op S is more like hardware specific. We will explain more in the following video. So without overdo, let's jump to the content. Let's first talk about the model size. We will, in this example, we use ResNet as example, try to explain to you how the model size is calculated. So assume the ResNet we're using precision floating point 32, and the model size is calculated using this formula, number of a parameter times the bit width. For floating point 32, the bit width is 4. The number of a parameter is the thing we need to figure out in order to calculate or to estimate the total size of the model. If we're taking this ResNet 50 as an example here, uh, the first layer is this COM layer 1. It has the kernel size 7 by 7. And because the input for the ResNet is RGB, so it has a 3 channel. So we need to use 7, the kernel size 7 times 7 times 3, and then times 64. That's the output channel. So we repeat the same calculation for all the conv layer as they listed here. And then the last layer in the ResNet 50 is the fully connected layer. The way to calculate the fully connected layer number of parameter is basically is equal to the input number times the output number. In the ResNet 50, as they mentioned here, the output, the last layer of the conv 5 output is 2048, and the output of the fully connected layer is 1000. So we use these two time together. So that's the number of parameter for the fully connected layer. So sum all of them together, we got approximately 25.6 million parameter. And then using that times the bit width 4, we have approximate 100 million. That's the um, that's the size of the model. After we figure out the size of the model, another memory-related metric to consider is the activation, total number activation, and peak number activation. As I mentioned before, the total number of activation is mainly concerned in the CNN training because we need to save all the activation for backpropagation. And for CNN inferencing, we need to save both the input activation and the output activation in the memory because the inferencing is like a sequential operation. We need to make the output activation in the memory as well to make it ready for the following calculation or following layer. So in the inferencing, the memory should be enough, more than the peak memory requirements. As we show here in this plot, the layer number 2 has the highest memory requirements, so the total number of memory should be more than that. That's the minimum threshold memory has to exceed in order to run the model properly. Number of activations. Here we gave two examples, fully connected layer and 2D convolution layer. We show how to calculate the memory consumption for inference. Here, for fully connected layer, we have a number of input plus number of output. These are the activation we need to have in the memory, and then times the bit width. That's the precision we use for each of the activation. So in total, this is the memory consumption for inferencing. When it comes to the 2D convolution layer, we actually need to figure out the input tensor dimension. In this case, we choose this dimension. That's the dimension needed by the ResNet. And we assume the 3x3 kernel size, output channel 64, stride 2, and padding 1. With this information, we could use this two formula to calculate the dimension of the output. And also since we defined the 64 channel here, so the third dimension here is the 64. So this is actually the output dimension we have here. Then again, we plus the input activation and output activation, plus them together, then and times the precision. So this is the total memory consumption for inferencing for this particular layer. When we have a very deep neural network, we may have many convolution layer and many fully connected layer. So we basically need to repeat this calculation for each of the layer to understand which layer has the peak memory consumption for inferencing, and then make sure our memory is available more than the peak value required by that particular layer, so that we can run this neural network for inferencing smoothly on the hardware. So far, we have talked about the memory-related metric. Now let's jump to the computation-related metric. MAC is the first concept we need to introduce here. So MAC represents multiplication and accumulation. If we take a matrix vector multiplication as example here, what we are trying to do is that we need to calculate this A times V here. The A has a dimension m times n here, and we need to do this dot product like this m times in order to achieve this new vector. If we look at this dot product, we see we are going to do n times multiplication and also n minus 1 times accumulation. So all combined together, this actually equals to n MAC here. So that basically tells us for one dot product, one element in this array or in this vector, we need to do n MAC. Now we have m elements here, so in total it's m times n MAC here. For matrix multiplication, that's basically the same thing, but we need to think about another dimension, which is the k. For example, we have m here, and then we have a k here. This is the first matrix dimension. Then after that, the k must be matching to this k here. Then we have an n. So in total, we need to do n times m times k MAC for matrix to matrix. After we have the MAC, we can convert the MAC to flop. Flop means floating point operation. So because each MAC have multiplication and accumulation, so that in total that's two floating point operations. So we need to use this formula to convert MAC to flop. And flop S is more hardware specific. It tells us that how many flop operation a hardware can perform in 1 second. Op including not only the floating point operation but also the integer operation. So that's the difference. Here we give two examples how to calculate a MAC for fully connected layer and a 2D conv layer. For fully connected layer, it's basically same like the matrix vector multiplication we mentioned before. So we have a number of input that's m and number of output that's n. So the number of MAC is simply m times n. When calculating the uh, convolution layer, the number of MAC etc. depends on the input. So assume we have an input tensor with this dimension, and then we have an output tensor, which is going to be for this dimension. So assume that the output will have this volume with the dimension we mentioned here. So for each of the elements in this volume, we need to do some calculation. So this is actually the amount of calculation we need to do per kernel, because we need to use the kernel to times to the input, and so in total, in order to achieve one of these elements, this is the amount of calculation we need to or amount of MAC we need to do for this one element. And in total, in this volume, we have this many of elements. So if we want to calculate the total MAC, so this is the result, how to calculate MAC. Here is a summary of the DN commonly used component. They're including the number of parameter for each of them and also the MAC when we how to calculate them. So there's a couple of things I want to mention in these slides. The first thing is about this one here. They are representing the number of bias. So for fully connected layer and the convolution layer, we have a bias parameter that's a learnable parameter for each of the outputs. So that's why we have a one adding here. So that makes the total number of bias equal to the output size. Same here for the convolution layer and also the group layer. And for the batch norm activation function and pooling, the batch norm, we have a two learnable parameter. That's basically used to compensate the normalization. After the normalization, we may lose the precision. So we need to have this two parameter to compensate that one. So for each of the input, we will have these two parameter. So that's why we use 2 times C in here. That's the input channel. Activation function and pooling layer, there's no learnable parameter. So that's all for today. Thank you for watching.